Alrighty, PChem, this is kind of a totally optional video for you, but I wanted to go over a couple topics that I think that you guys struggle with a little bit, and one of the quick ones is Coulomb's law. So Coulomb's law talks about the strength of an ionic attraction, and the stronger things are attracted to each other, the higher melting points they have, the higher boiling points they have, and the harder it is for something to dissolve. So if a chemical has a really strong ionic attraction, it means that probably something's going on with Coulomb's law that keeps it attracted. So Coulomb's law generally is Q1 being the charge of your first ion times Q2 over R squared. So Q1 and Q2, those are our charges. R is our bond length. And so there are kind of two different things that you're going to see, two different types of questions they're going to ask you. They're going to ask you to compare compounds that have two different charges or compounds that have two different bond lengths. So for example, if we take a look at an NaCl versus KCl. Okay, so in this situation, in your Coulomb's law argument, there are always two issues at hand. There is the charge component of the argument and the size component of the argument. And so the first thing you always want to do is you want to find the charge of the elements in there. So Na is a +1, Cl is a -1, K is a +1, and Cl is a -1. So if we look at this, they all have the same charges. Na, K, the same, Cl, and Cl are the same. And so when we do the Q1 times Q2 for both of these, it is always going to be a +1 times a -1. So that part is not relevant for our argument. However, in our argument, the size is different. So this is where we have to kind of pay attention. Because of its location on the periodic table, Na is 1 period higher than K. And this means that Na is going to have a smaller radius than potassium. Hopefully you know your periodic trends well. It's really super duper important for your Coulomb's law. So Na has a smaller size here, which means that the distance, if we think about an Na to Cl bond, the distance between the two nuclei here are going to be smaller than if I would do the same, get a teeny tiny ruler and do the same thing for KCl. Because K has a bigger radius, the distance between here is a little bit bigger. And the bigger the distance between things, the less strongly they're attracted to each other. So when I look at this R squared at the bottom here, that distance is going to be smaller for the Na than it is for the K. And if I have a smaller number on the bottom, it means I get a bigger overall energy for my bond, and so it is stronger. So the general idea is that if I have smaller elements involved in a bond, I am going to have a stronger bond than if I have a larger element. The other type of thing that you could potentially see is a CaCl2 versus KCl argument. So in this situation, again, I always check charge first because I think it's the easiest. So calcium is a +2, Cl is a -1, K is a +1, Cl is a -1. So in this situation, we have a +2 for our cation and a +1 for our cation. In the Coulomb's law argument, Q1 times Q2 over R squared. Ignore my R there, it's a little sloppy. Okay. If I take a look at these two things, in this case, the calcium, because it has a +2 charge, is going to have a higher energy value than something that has a +1 charge times the -1. So we've got a bigger number on top here. If we look at potassium and calcium, they are very close to each other on the periodic table, and so they are going to have comparable radii, but in the case of their charge, the Ca has a larger charge. So what's going to happen is the calcium is going to form a stronger bond because it has a +2 charge. Hopefully that gives you a quick review of Coulomb's law. If you have any other questions, come to a meet and we can answer them.